A modern AI rack is one of the most power-demanding systems in today's industry. It is where conventional data center power architecture cannot deliver. I'm David Kudelasek, and in this wall, ST shows complete portfolio for AI data centers from the grid to the GPU. It divides the architecture into three segments: direct AC-DC power supplies on the left, dedicated DC-DC solutions in the middle, cooling on the right. All of these solutions are fully in line with ODMs and hyperscaler specs, which is not something many companies in this sector can say. This section shows a conventional server rack. Input single-phase AC is converted at the rack level by an AC-DC stage with the 50-volt output. The 50-volt bus bar distributes the power inside the rack. Each server has a DC-DC step-down stage from the 50-volt down to 12 volts and from the 12 volts down to the GPU voltage. ST offers two reference designs for the rack front-end power supplies, an 8.4 kilowatt unit and a 5.5 kilowatt unit. Both include a hold-up extension capability, so the rack runs through grid disturbances without dropping the load. This architecture is high efficiency, very high power density, and it is possible due to the optimal combination of specific technologies: silicon carbide input stage, backed with gallium nitride for the hold-up extension, and silicon for secondary stage and the logic. This is the 800-volt HVDC story. The arithmetic is simple. At 50 volts, delivering 1 megawatt means 20,000 amps. With current that high, conductive losses became excessive. At 800 volts, the same 1 megawatt is just over 1,000 amps. Simple Ohm's law, saving a lot of copper wiring. Three architectures are presented here. The first is the centralized high-voltage AC-DC sidecar, a 1 megawatt converter that takes grid AC to 800-volt DC and serves multiple racks. The argument is that a single high-power converter serving many racks is more efficient than many smaller converters in every rack. The second is a server rack with centralized DC-DC, an 800-volt to 50-volt conversion at 250 kilowatts that feeds a 50-volt bus bar inside the rack. Then each server steps down from there. The heavy lifting stage sits outside the server, while the existing rack interface stays familiar, the very same 50-volt bus bar as in conventional solution, so no need to change the servers. The third is localized DC-DC architecture. 800 volts run directly to each server, with 800 volt to 50 volt and 50 volt down to 12 volts happening per server. High conversion density per unit, fully modular. These are the specific products for this architecture. The 800 volt down to 12 volt 6 kilowatt DCX power delivery board skips the 50 volt completely and offers direct conversion from the HVDC, representing the most advanced trend of this architecture. The 800 volt to 50 volt DCX 12 kilowatt and 50 volt to 12 volt 1 kilowatt represent solution with standard 50 volt rail. As these are made for extreme power density up to 2.6 kilowatt per cubic inch, it is mainly gallium nitride handling the switching frequency of 1 megahertz. But still, our sub-milliohm silicon MOSFET are still used for the 12 volt output stage of the 6 kilowatt board, outperforming the other technologies. To supply the GPU from the 12 volt, the converter must be as close as possible And for that purpose, we have the 12-volt POL board. It is a 16-phase topology based on ST's fully digital multi-protocol controller for the different GPUs. To ensure safety during undervoltage, we have an eFuse solution with a hot swap feature up to 30 amps at the 50-volt rail. What gets missed in discussion about AI servers is that cooling has become a problem. AI rack heat output scales with input power. The cooling system must grow with it. Conventional air cooling reaches harsh ceiling somewhere around 50 kilowatts per rack. Past that, the industry moves to liquid loops driven by heat pumps. These are more environmentally friendly than the evaporative systems, which are known for their high water consumption. And heat pumps need motor drives. The three solutions on this panel are 4 kilowatt, 7 kilowatt and 10 kilowatt heat pumps. The 10 kilowatt uses three-phase Vienna PFC and the motor control based on the same ST silicon carbide MOSFETs we have seen in the power supplies. The 4 kilowatt and the 7 kilowatt boards implement interleaf PFC and dual or triple motor drive, accommodating both compressor and fan drives on the same board, which are handled by ST's compact and efficient intelligent power modules called SLIMs. This wall represents ST's coverage of the AI data center power chain. From the grid side AC/DC through the 800-volt HVDC backbone into per server DC/DC and across the cooling loop that removes the heat the rest of the infrastructure generates. The portfolio is intentionally mixed across the technologies. Gallium nitride for the highest switching frequencies, silicon carbide for the heavy power stages, silicon for lower voltage and support electronics. Each conversion stage gets the right device for the engineering problem it is solving. AI data center power has to be one of the most demanding applications in the commercial power electronics today. The architecture is moving fast. The numbers of the power are climbing. The design margins are shrinking. ST's portfolio meets all three pressures at every conversion stage of this wall, making it higher efficiency, better power density, and overall better for the environment.